Thanks very much. I'm Dave Blei from Colombia. Je peux parler un peu français, mais trop lentement parce que, yeah, anyway, I'm done. So, I got B's in French all through high school. I'm going to talk today about scaling and generalizing approximate Bayesian inference. Thanks very much to Nicolas and Florent for inviting me here. It's a pleasure to be here. So I'll just start with a little bit of background. So in a lot of situations we might be in applied data analysis, we have complicated data and we want to make sense of it. It might be data about science or text data or data about people purchasing things or social network data. This is a general problem in machine learning. And what I work on is probabilistic machine learning. It's also applied Bayesian statistics. They're sort of synonymous, where the idea is to build statistical machine learning methods that help us connect our domain knowledge about the data we're trying to analyze to the method that we're using to analyze the data. And our goal in probabilistic machine learning very broadly is to build this methodology so it's expressive, so we can express our assumptions about the data easily in a machine learning method, scalable so we can handle large data sets, and easy to develop so that we can do it quickly and without a lot of extra work. So just some examples. These are from our own research in my lab, just because I had the pictures handy. This is an example of taking in a big network of, in this case, patents and finding community structure in this big network. This is an example from population genetics, where you take in genetic information about millions of people, maybe 1 million people, and then estimate the ancestral populations that mixed to form them. This is an example we did with economics data. This is people purchasing things at supermarkets, a big data set of hundreds of thousands of supermarket trips. This was done with an economist. And here, this picture is like an embedding of the items in the supermarket. And this was exciting to the economist because it showed us that crackers and cheese go together, which probably in Lausanne, you know that. So these are all just examples of probabilistic machine learning where we follow what I like to call the probabilistic pipeline. We take our assumptions and knowledge and a question about a data set. We build a probabilistic model. This is a graphical model with hidden variables being unshaded and observed variables being shaded. And then we take our data and our model and we try to uncover the patterns that live in the data and then use those patterns to form predictions or interpret the data set or do whatever it is we were trying to do in the first place. And so this is kind of how I like to think about these different applications, applied problems, where we take our question, build a model, uncover patterns, and then use those patterns. Now, what I want to talk about today is posterior inference. So when I'm playing this game, my algorithmic problem is, given the data and my model, what is the conditional distribution of the hidden elements that I assumed live in the data, given the data I observed? That's the posterior inference problem. In plain English, this answers the question, what does this model say about this data? And what I want to talk about today is how to answer that question in a scalable way, meaning with many, with big data sets, and also how to do it in a general way, meaning whatever model I dream up with my domain expert, I can apply posterior inference and uncover the hidden variables given the data in that model. Make sense? So, just some background. How does Bayesian statistics work, or probabilistic machine learning? Well, we set up a joint distribution of hidden variables z and observations x. And then all of our inference about the data happens through the conditional distribution of the hidden variables given the data. Okay, and that, of course, is the ratio of the joint to the marginal of the data. And this is Bayesian statistics in a nutshell. Just to be clear, we're not getting into any fights today. We might later, but there's no need to be Bayesian to calculate a posterior. It might be that your boss told you to calculate a posterior, or for whatever reason you want to get this conditional distribution of hidden variables given observed. It's not like you're taking a philosophical stance when you do that. All right. The problem, of course, is from a practical perspective that for most interesting models, for most models that we might want to fit, the posterior is not tractable. And so we have to appeal to approximate posterior inference, and that's what variational inference is all about. So you remember one slide from this talk. this would be the slide I would want you to remember. This is what variational inference is. Okay, so remember, we're in that Bayesian setup, P of z and x, and we want to get P of z given x. And imagine that the space of the slide are different distributions over z. And here is the posterior that I care about, P of z given x. Okay, this is the posterior for the model that I asserted and the data that I saw. What variational inference does is sets up a big family of distributions over z called Q, and it's parameterized by the parameters nu, variational parameters, right? So every point in this ellipse is a different setting of the variational parameters. And then we optimize the variational parameters to find the member of that family that is close to the exact posterior. Okay, that's variational inference. Then we use Q of z with parameter nu star as a proxy for the exact posterior that we can't calculate. Okay, and every paper about variational inference that you read is somehow doing some form of this picture. Maybe it's changing the optimization algorithm or the measure of closeness or something about the variational family, but this is the picture for variational inference. I didn't mention the measure of closeness is KL divergence. Okay, KL between Q and P, although that's something that could be changed too. Please feel free to interrupt me with questions if you have questions. Okay, so as an example, let's look at a classical probabilistic model, the mixture model. So this is a mixture model where I have data X. Each data point comes from some cluster assignment, one of K values, Z, and it comes from a distribution indexed by that value. All right, so like a mixture of Gaussians, mixture of 10 Gaussians is a mixture model. Relates to K-means, and it's a probabilistic machine learning method for clustering data. Now, even in a simple mixture model like this, the posterior distribution of the mixture components and the mixture assignment for each data set, each data point, is not tractable, and so we can use variational inference to approximate that posterior. And here's what that looks like. So let me explain this picture. So here, if you can look behind this gray circle, you can see a data set, all right? Now, these are data points in 2D, and they're colored with different colors according to what cluster they really came from in the truth. Okay? Is that right? Yes. Now, the model just sees the locations of those data points, and the goal of the mixture model is to cluster them into whatever it is, 5 clusters. Okay? Let's say we know that number K in advance. We want to approximate the posterior distribution of the locations of the clusters and the assignments of data points to clusters. And what variational inference does is it approximates that posterior by solving an optimization problem. All right, so these gray contours is like the posterior predictive distribution of the next data point according to the variational approximation. And you can see that as variational inference proceeds, it gets better and better at fitting the true data set. All right, so what happened here was I took this data, I took a mixture model, I asked for the posterior, and here I'm plotting the corresponding posterior predictive. All right, this is a track of the variational objective. We'll talk about what the evidence lower bound is in a little bit, but this is like the KL divergence between Q and the true posterior. And you can see that it's getting closer and closer and closer as we proceed with the optimization. Okay, so that's variational inference. And if you're familiar with MCMC, you can contrast this with MCMC, where we sample from a Markov chain whose stationary distribution is the posterior we care about. Here, we target the same posterior, but try to get to it through optimization. Okay, I think that my talk is too long to go into this, but variational inference has an interesting history. These are ideas that really came from statistical physics in the 80s and migrated to machine learning and graphical models throughout the 90s and 2000s, including to things like Bayesian neural nets. But if you want to ask me later, I can talk more about that history. Okay, so what I want to talk about today is how stochastic optimization makes variational inference better. In particular, stochastic variational inference scales up variational inference to very large data sets, and black box variational inference generalizes this story to a wide class of models, and both rely on stochastic optimization. All right, so first, stochastic variational inference. How can we scale up variational inference to very large data sets? We want to play this game, but of course our neuroscience collaborator or whoever has a massive data set. And so how can I use VI with a very large data set? To tackle this problem, we're going to kind of generalize the class of models that we're working with. And I want to define this class called conditionally conjugate models, right? So here's the graphical model, and here's the corresponding factorization of the joint distribution. We have P of beta, a latent variable, and then conditionally independent P of z and x, where z is latent and x is observed, given beta. Okay, this is called a conditionally conjugate model. We're going to place some conditions on it. The observations, the data is x, x1 to n. We call z local latent variables. These are hidden variables, and I'll explain the difference in a second between local and global. And beta are called global hidden variables. And the difference between local and global hidden variables is that in the factorized joint distribution of the variables in this model, the ith data point xi only depends on zi and beta. All right? And you can, if you know graphical models, you can see that and read that off the graph. Right? Xi only depends on Zi and beta. In particular, it does, given beta, it does not depend on other Zijs. Of course, our problem is to calculate P of beta and Z given X. That's the posterior of the hidden variables given the observation. All right, we need a little bit of jargon. A complete conditional is for each latent variable, the distribution of that latent variable given all the observations and all the other latent variables. We call that the complete conditional, okay? And we're going to assume that each complete conditional is in an exponential family. If you're familiar with an exponential family, great. If not, it's a concept of probability distributions that encompasses things like Gaussians and gammas and Dirichlet's and Poissons and categoricals. All the basic distributions that you know probably are in the exponential family. Okay, it's a way to think generally about that big class of distributions. Okay, and so we're going to assume that each complete conditional is in an exponential family. Just think of a Gaussian, for example. P of beta given z and x is in some exponential family, which has a parameter, eta sub g is the parameter of the exponential family. That is, of course, a function of what we're conditioning on. And P of zi only depends on beta and xi, because remember the difference between local and global variables, and that's also in an exponential family with its parameter that depends on what we're conditioning on, in this case, beta and xi. Is this clear? So, for example, you have a model, and you imagine that each complete conditional is a Gaussian, and it has a parameter that's some function of z and x. Or this complete conditional might be a gamma with some parameter that's a function of beta and xi. Okay? Good. That's a condition. That's the class of conditionally conjugate models. Now, it turns out that that kind of abstraction of conditionally conjugate models describes a lot of the probabilistic models for unsupervised learning that you might have read about in the 90s and 2000s. Things like mixture models and time series models and factorial models, matrix factorization, even Bayesian nonparametrics models, hierarchical regression models, some of them. A lot of these models have the flavor that you can write them like this, and moreover, you can write the complete conditionals as exponential families. Okay, so what we're going to do is solve variational inference for large data sets in that big class of models. Okay, again, here's this picture. We want to minimize the KL divergence between Q, the variational family, and the exact posterior that we're targeting, P of beta and Z given X. I feel like I could have done this in French. Okay. The KL divergence is intractable, right? You might have noticed that it involves the thing that I said we can't calculate, P of Z given X, or P of beta and Z given X. Okay? And so in variational inference, what we do is we optimize what's called the evidence lower bound, or the elbow, instead. And the evidence lower bound is equal to the KL divergence plus an additive constant when we, or the negative KL divergence more accurately. And so when we maximize the elbow, we are minimizing the KL divergence. All right. And the elbow is intuitive. So here's the elbow. Let me just go over here. It's a function of the variational parameters. It has two terms. The first term is the expected complete log likelihood. The complete log likelihood is the log probability of all the hidden variables and the observations. And this is the expectation of that with respect to Q, which remember is a distribution over beta and Z. And then the second term is the negative entropy, okay? Expectation log Q. Clear? The first term wants Q to place its mass on configurations of beta and Z that have high log joint, right? In other words, it'll put all its mass on the map estimate. The second term wants Q to be diffuse, right? It wants Q to have higher entropy. In other words, for it to be more varied. And so kind of trading off these two terms is what the elbow is doing. But those are just intuitions. Mathematically, the elbow is equal to the KL divergence plus an additive constant. And so optimizing this is equivalent to minimizing the KL, which is what we're trying to do. Okay, but you'll see in papers about VI, the elbow is the main objective function. One small caveat that we're not going to worry about is that the elbow is not convex. Okay, but we should worry about that, of course. All right, we're almost done, but not quite done. We have a variational objective function, but what about this family Q? All right, so Q of beta and Z defines the variational family, and we need to set up what that family is. It can't be all distributions over beta and Z, because if it was, we would then find the actual posterior, and we know that that's not tractable. So the game in variational inference, the practical game, is to somehow limit the variational family to still be expressive, but for the elbow optimization to be tractable. And there's lots of ways to play with this, but what we're going to do here is use the factorized or mean field variational family. It's really the simplest one. And that one says that each variational factor, each latent variable in Q is independent, and each one is governed by its own variational factor. Right? So Q of beta has its own variational parameter lambda, and then independently Q of Zi, each Zi has its own variational parameter Bi. Right? And just meditate on that for 1 second. Like in the mixture model case, I have the mixture locations, and then every data point is assigned a mixture component. And so what this is saying is that each mixture location has its own variational parameter, right? For each of the K mixture locations, I have a different variational parameter, but also every single data point has a variational distribution over which mixture component it's assigned to. All right, so data point over here has a phi, data point over here has a phi. So this looks crazy, but it's pretty expressive because it can really describe any configuration of mixture components and assignments of data to clusters. Okay. Furthermore, each of these factors is going to be in the same family as the model's complete conditional. Okay, so remember, we already decided in our model that the complete conditionals were in the exponential family. And so if P of beta given Z and X is a Gaussian, then Q of beta is going to be a Gaussian with free mean and variance parameters. Okay, if this is a categorical, this will be a categorical with a free categorical parameter. All right, and now we have completely specified the variational inference problem. We have an objective function. We have a variational family. It's parameterized by this stuff, and we can optimize. Any questions so far? Okay.
Yeah, and
What's that? Yeah. Yes, that's right. So the Z's in the posterior, the Z's are determined by beta and X, but yes, there is a latent Z for every data point. That is true. Well, we don't get to control what we like. That didn't come out right. The model is specified in advance. Yeah. But yes, that's the idea of a local variable. But this happens all the time. In mixture models, Z is the assignment of each data point to a cluster. In something like probabilistic PCA, Z is the low dimensional representation of the high dimensional data point. In a topic model, Z might be the topic proportions in a document collection. And so this is a common setup with these local variables. If you're a statistician, I don't know if you're a statistician, you're not. Okay, if you were a statistician, then you might usually see a mixture model with Z implicitly marginalized out. A statistician sees a mixture model as the sum over K equals 1 to K of P of X given that cluster. But here we're just explicitly writing down that local lake variable. Yeah. Good, but that's a great point, that Z is growing with N. Yes. Okay. So we've completely specified the elbow. We now have a function of lambda and phi, all the phis, phi 1 to n. And here it is, the elbow as I showed you. And now what traditional variational inference does is uses coordinate descent. Okay, I have variational parameters lambda, I have n variational parameters phi 1 to n, and I just march down my arm, iteratively optimizing each variational parameter while holding the other ones fixed. Okay, that's classical coordinate descent variational inference. And it turns out that the updates have a very nice form. If you write down the exponential family form of your complete conditionals, then the update for each variational parameter is the expectation under Q of the natural parameter of the corresponding complete conditional. And the factorized family, where everything is independent, plays nicely with this, because that means that the right-hand side of the expectation, which is of course a function of the other latent variables, is going to be totally disconnected from the left-hand side, the parameter of interest, because all these variables are independent in the factorized variational family. Good. That's variational inference. Iteratively update each parameter, holding the other ones fixed. Notice again, if you're familiar with MCMC and Gibbs sampling, notice the connection to Gibbs sampling. In Gibbs sampling, I iteratively sample from these complete conditionals, and with a completely different set of mathematics, we have a very similar algorithm that iteratively sets these distributions to the expectations of the parameters of the complete conditionals. And here it is as a little flow chart, taking my data set, update all the local parameters, given the global variational parameters, then update the global variational parameters, which looks like an aggregation of these local variational parameters, and repeat this to climb the elbow. Right? And this is how we made this picture of the mixture model. This is how we did variational inference in the mixture model. Okay, but the problem is that this classical method for variational inference is inefficient for large data points. Why? Because you have to do local computation for each data point, then aggregate those computations to get the global variational parameters and repeat. So just if I can do this in English with the mixture model, what would I do? I have my current idea of where the mixture components are. I march through all these data points, figuring out what their distribution of which mixture component they came from is. Then I aggregate all of those calculations to get a new idea of the mixture components, and then I repeat going through all of them again and again and again. Okay, and this works for 100 data points or whatever we have here. But if we had 1 billion data points or something like that, then this quickly becomes intractable. Okay, so that's what motivates stochastic variational inference, which will look like this. We have a big data set. We have a model. Again, we're going to subsample our data. We're going to infer the local variational parameters just for that subsample, and then we're going to update the global variational parameters, okay, with the results of that little, the results from the subsample. All right, and we're going to repeat that. And that's going to be a stochastic optimization algorithm on the elbow. All right, so how do we get there? Of course, we use stochastic optimization. This is Herb Robbins. He was the chair of the Columbia Statistics Department at some point, and he invented stochastic optimization in 1951. And in this famous paper by Robbins and Monroe. He also invented bandits and empirical Bayes. So he's amazing. I wonder what he was smoking, because I would like to find that brand of tobacco. Good. So what is stochastic optimization? We're all using it every day, all the time, even when we're sleeping. It is to replace the gradient in some kind of optimization with a cheaper, noisy estimate of the gradient. And it is guaranteed to converge to a local optimum of our objective function. All right. This is the algorithm that has enabled modern machine learning. It's letting us fit massive models to massive data sets. All right. More technically, stochastic optimization. I know that here at EPFL, everybody knows stochastic optimization and drinks it in the water, but still, it's on my slides. We take the next estimate of the variational parameters equal to the previous estimate plus some step size, rho t, times a noisy gradient of the elbow. And what conditions do I need on that noisy gradient? I need that it's unbiased, meaning the expectation of that noisy gradient relative to the noise in the gradient is equal to the exact gradient that I would follow if I had the time. And classically, we require that rho t follows the Robbins-Monroe conditions, but of course, all of you know that in modern times, we use adaptive step size schedules. And in fact, we don't even know how they work. We just call them in libraries in Python. Okay. So how are we going to apply this idea to variational inference? First, let me spotlight for you what is the problem. It's in the global variable. So thanks to exponential families and this very beautiful Bayesian theory about conjugate priors and likelihoods, the complete conditional of the global variable has this form. All right, so this is the probability of beta given z and x in that whole class of conditionally conjugate models, it's going to have the following form: alpha, which is some hyperparameter, plus a sum over all of my data of some function, I called it t, of zi and xi. Okay? And so if you're familiar with it, this is like classical results around Dirichlet multinomials or Gaussian Gaussians or beta Bernoullis or gamma Poissons. They all look like these two equations, okay? Where we have a exponential family prior and an exponential family likelihood. If they play nicely together, the posterior is going to have this form. Now, what does that mean for variational inference? Well, it means that the coordinate ascent update for the global variational parameter is, again, my hyperparameter alpha plus a sum I equals 1 to n of the expectation under phi I of this function t of zi, z is now capitalized because it's random, and xi. Clear? And of course, you can see just by staring at this that for large data sets, this is going to be really expensive because I have to sum over n is a billion. So how do we apply Robbins's brilliant idea? There's a detail here, which is that the natural gradient of the elbow, not the usual gradient that you think of, but the natural gradient, which is the gradient warped to accommodate the fact that we're optimizing the parameter to a probability distribution. The natural gradient has this very nice form. It is essentially that coordinate update here minus lambda. Okay, the natural gradient has all kinds of great reasons for using it, but the reason we're using it here is because it's simple and it lets us do stochastic optimization easily. Now, we just do classical mini batching to get a stochastic optimization. Sample a data point at random, scale up the contribution of that data point to the natural gradient, and then follow that gradient. This is good for stochastic optimization. It's obviously unbiased. If you take the expectation of this, you can see that you get the actual gradient. And it's cheap because it only requires calculating the optimal local variational parameters for one data point. Okay. All right, so as an example, we'll look at a topic model, latent Dirichlet allocation. All right, so this is like a mixture model, but it's a mixed membership model. It's a model of document collections where now the global latent variables are topics, distributions over words. The data set is a bunch of documents, and the goal is to uncover the topics that describe these documents under what are called mixed membership assumptions, meaning that the words of the documents come from multiple different topics, and each document has its own separate distribution of topics. Okay, so it's capturing the fact that, like, if you had a newspaper, some articles will be about sports and business, and others will be about sports and health, and others will be about health and business, and you capture that heterogeneity in your data set with this hierarchical mixed membership model called latent Dirichlet allocation. Those details, though, aren't important for this talk. So here's an example. You take 2 million articles, 1.8 million articles from the New York Times, and you ask for the posterior distribution of the topics, the distributions over words that generated them under those assumptions, and this is what you get out. So you can see that just by taking in the data, you get distributions of words that correspond to recognizable subjects that are discussed in the newspaper. Okay. Now, with classical variational inference on a laptop, which is what we were doing this on, you can't calculate the posterior for 1.8 million New York Times articles, but with stochastic variational inference, you can. And this is why we would want to do this. And this is a picture that you see about stochastic optimization all over the place, that as you compute more and more and more about your data, using stochastic gradients and following these noisy gradients, you get to a much better place when you've done as much computation as you have for just one iteration of a classical coordinate optimization algorithm, and those benefits continue. Okay, this is the idea. And in the context of variational inference, stochastic variational inference let us scale up these community detection models to very large networks, and let us scale up these important models in population genetics to massive data sets of individuals. Okay, and again, I derived this algorithm for you for this big class of models that encompasses mixture models, Bayesian nonparametric models, all these different models. If you have a model that you want to fit, and it is in this class of completely conjugate models, then now you can do Bayesian inference with a very large data set. That's the idea. And this is like the history slide. I don't have so much time for this, but this idea really grows out of the ideas of scaling up EM with stochastic optimization. That was people like Eric Lean and others have worked a lot on that over the years. All right, so that's the first part of my talk, so about stochastic variational inference. We have until 3. Okay. So in the second part of the talk, I want to talk about another application of stochastic optimization to variational inference, which is called black box variational. All right, so here's the idea. This is a picture of the appendix of the paper about latent Dirichlet allocation. That model I just showed you, we applied stochastic variational inference to. And everyone here was not even born, but like back in 2002 and 2003, when you wrote a paper about variational inference, you had to include an appendix like this. And that appendix derives the elbow, takes gradients of the elbow with respect to the variational parameters, uses Lagrange multipliers sometimes if needed. You can look up what those are. And forms the algorithm, the variational inference algorithm, based on all these painstaking computations. And so I spent all of grad school writing appendices like this. And the problem with appendices like this is that there's always a mistake. And in fact, in this appendix, there is also a mistake. But I'm not going to show it to you. The idea behind black box variational inference is to be able to use variational inference without writing appendices. Right? We want to be able to easily use variational inference with any model without requirements of conditional conjugacy and things like that, and without having to write appendices. We still want to be able to perform inference with massive data, but again, we want no mathematical work beyond specifying the model, right? So this is the dream, that there's this black box. In retrospect, it was a bad metaphor because it kind of implies that we're hiding something, but it's a transparent black box. There's a black box, in comes your data set, any model you can dream of, and a bunch of reusable variational families, and out pops your estimate of the posterior. So that's the idea. And even though I gave you this nice, impressive list of conditionally conjugate models, in fact, the models that are not conditionally conjugate is even longer. Okay, and it includes some really simple models like even logistic regression. I don't even know if I put it on here, but also deep learning models like Bayesian neural networks and deep latent Gaussian models, models with attention that are, of course, very important these days to fit. Generalized linear models where you don't have special structure in the response distribution, cousins of topic models like correlated topic models and dynamic topic models. Many, many models, stochastic volatility models, do not satisfy the conditions that the first half of the talk required. All right, and so we want to be able to do variational inference in this bigger class. So in general, the idea behind BBVI is the following. We're going to write the gradient of the elbow, the same elbow, as an expectation. We are going to then sample from Q to form a Monte Carlo estimate of the gradient. And then we're going to follow that Monte Carlo estimate in a stochastic optimization, right? It's intuitive that a Monte Carlo approximation of a gradient construed as an expectation is a noisy gradient, right? Because the expectation is going to be unbiased. And so here's what that looks like. Draw samples from Q, make a Monte Carlo estimate of the gradient of the elbow, follow it, and then repeat the process with your new Q. Right? In designing this algorithm, we want to keep in mind the black box criteria, where we should only need to sample from Q, evaluate things about Q, and evaluate the log joint. All right? So intuitively, if you only needed to do these things, then evaluating the log joint is like specifying the model. And these things can be reused across models. And so now you can do variational inference in whatever model you dream up. To be clear, there are models that people are interested in, especially in fields like epidemiology and climate science, that you cannot evaluate log p, right? So these are like these physics simulators that are written in Fortran from the 70s and spit out samples from some complicated physics theory that you still might want to do inference on the latent variables governing governing your data under that model. This does not accommodate that. That's a different idea. That's a different class of problems. But for many, many models, just doing this would open up the door to doing easy variational inference. Okay, so of course I haven't told you anything yet because one of the steps was to write the gradient of the elbow as an expectation. How do you do that? There's two ways. The first way is called the score gradient. This is the gradient of the elbow equals an expectation under Q of a product of two terms, right? The second term, we're calling it the instantaneous elbow. It's log P of X and Z minus log Q of Z, right? This is the elbow without being wrapped around an expectation. The first term is the score function. There's a lot of confusion about the term score function, and it's going to be even more confusing in this talk because we're going to use both types. But the score function in this slide is the gradient of log Q with respect to the variational parameter, okay, at Z, right? So at Z, which way does the log of the density of the variational distribution point is what this is, okay? And, you know, you can kind of see that this is intuitive. For a Z where the instantaneous elbow is big, we want to move the variational distribution closer to have that Z with high probability because that'll make the expectation of the elbow big. When the instantaneous elbow is very small, we might want to move away from that. Okay, but again, that's just intuition. Mathematically, this is the gradient of the elbow. And this way of writing gradients has come up in a lot of different parts of AI and machine learning over the years. It's also called the likelihood ratio or the reinforced gradient. And this, by the way, is also the same kind of gradient and objective function that is used to do fine-tuning of large language models. They use this reinforced gradient, or I like to call it a score gradient. Okay. That's the first way. And notice that this satisfies the black box criteria. In order to take a Monte Carlo approximation of the score gradient, I just need to sample from Q, evaluate the score function, which I can figure out how to do once and for all, and then use that variational factor in a lot of different models, and evaluate the log joint and log Q. Okay, so this satisfies our criteria. Now, in practice, just using the vanilla score gradient isn't going to work. The reason being that the variance of the stochastic gradients that it gives is too high, and so the algorithm can go in a big step in a wrong direction. And so tricks to fix this are things like Rao-Blackwellization or conditioning, control variates, which is a way to reduce the variance of stochastic gradients, importance sampling. There's all kinds of ways to reduce the gradient, all staying inside the black box criteria. Of course, you can use adaptive step sizes like we always want to with stochastic optimization, and it plays nicely with stochastic variational inference, meaning within the BBVI algorithm, you can subsample the data if you have a very large data set. All right, so to give you an example of this at work, we're going to fit what we call a deep exponential family, right? And what this basically is a probabilistic model whose latent structure mirrors a deep neural network, where I have for each data point a cascade of latent variables, one after the other. These are like hidden units that bottom out in my observation. All right. In fact, in the history of deep learning, these kind of early deep neural networks were versions of this. Things like the sigmoid belief net. This is a generalization of the sigmoid belief net of Radford-Niels, just as a probability model. Okay. So here's the table. You've seen computer science talks before, so you know that we have to have a table like this where we do the best. And but that's not quite the story of this table. So what this table is the following. In that deep exponential family, we have a lot of choices to make. We can change the number of layers. We can change the types of distributions at the hidden units. We can change the priors over the weights of the neural network. And the whole idea behind black box variational inference is that we should be able to explore this big landscape of models without a lot of extra work, whereas in the past we would have had to write a separate paper about each one. And so what you see here is that we were able to make this table, that we could try out all these different types of hidden units as well as different types of priors on the weights and understand the model fit. This is with, again, a document model where the X are word counts, and we're looking at a deep neural network, like a unsupervised deep neural network of word counts. And it does better than other models for text. But again, that's not important. What's important is that all of this whole part of the table was done with black box variational inference. Okay, so that's the first type of BBVI. Second type is called the reparameterization gradient. All right, just to be clear, this comes from, I first was aware of this in the variational autoencoder paper. Okay, but it fits into this framework of BBVI. So now suppose, in addition to being able to calculate everything, we can differentiate log P and log Q with respect to Z, with respect to the latent variables. All right. And further suppose that our variational distribution can be written as a transformation. So for example, a transformation of a variable with a fixed distribution. So for example, epsilon comes from some fixed distribution. Z is equal to a transformation of a function of epsilon and the variational parameters, implies that Z comes from Q. All right, suppose we can write down our variational family this way. The example that you'll always see is the normal example. If epsilon comes from a standard normal and Z equals epsilon sigma plus mu, then Z comes from a normal with mean mu and variance sigma squared. Okay. Notice that the variational parameters are part of the transformation. They are not part of the distribution of epsilon. That's what's key about this. Okay. So if you're in this setup where you can differentiate these things, meaning that Z, of course, is continuous, and that you can write your variational family as a transformation, then you have the following gradient available to you. This is the reparameterization gradient, which is an expectation now with respect to that noise distribution of, again, a product of two terms, the gradient with respect to the hidden variables of the instantaneous elbow, and the gradient of the transformation with respect to the variational parameters. All right, it's very easy to derive this. In fact, it's just chain rule stuff. Once upon a time, this wouldn't have been considered a black box gradient because you have to take gradients. But of course, with auto differentiation, this becomes black box because I can auto differentiate these two terms to easily calculate the reparameterization gradient. And there's all kinds of ways to embellish this type of this gradient for optimizing the elbow. All right, and so using this is how we learn that crackers and cheese go together in this fancy discrete choice model of shopping carts. We did a big analysis of fMRI data with a complicated model that the neuroscientists wanted to fit, which unfortunately wasn't conditionally conjugate, using BBVI and reparameterization gradients. And reparameterization gradients are useful in what's called probabilistic programming. So I don't know if you're familiar with it, but in probabilistic programming, the idea is to make the dream a reality, that you program your model in a programming language and then compile that model down into an executable that takes data and spits out inferences of the hidden variables. Right. And so in Stan, for example, but also in things like Pyro, they use reparameterization gradients to do variational inference in these probabilistic programming systems. All right. And again, BBVI can now help us with a big class of models, although not all models. Okay, so I don't know how much time you want for questions, but in the last 5 or 6 minutes, I can talk about a little bit higher level things in variational inference. Again, this is the picture. We have assumptions, knowledge, and a question. We make a model. Our data and our model gives us a posterior. We use that posterior to do things. And today we talked about how to do this part, right? How do I calculate the posterior given a model in a big data set? Stochastic VI scales up this picture to large data sets, and black box VI lets us implement this picture on a wide class of models. This picture is nice too if you are a graduate student and want to do research on variational inference, because it kind of points to different ways that you can make this algorithm better. Or if you're not a graduate student but still want to do research on variational inference. So one thing is, of course, to expand the models VI can handle, going past this idea of differentiable or evaluable models? How could you work with what are called implicit models? Another idea might be to try to expand the class of variational approximations. So here we used factorized variational approximations, but of course, there's going to be a gap. As you make the variational family bigger, that gap in theory becomes smaller. However, this is counteracted by the fact that the elbow is not convex and the optimization becomes more difficult. And in fact, bundling up and understanding that whole messy set of ideas is an open problem in variational inference. Finding new methods for optimizing the variational objective. Here at EPFL, you are collectively world experts in optimization. And so how to use new optimization ideas to improve this useful optimization problem is an open area in variational inference. Exploring alternative measures of closeness between distributions. So here we use the KL between Q and P. We didn't meditate on it, but if you did, you would quickly see, oh, there's some things that are good about it and some things that are less good about it. And thinking about other types of distance functions between distributions is another open area in variational inference. Address and understand the limitations of VI, or more broadly, understand the theory behind VI. All right, so there is a whole campus filled with papers about the theory of MCMC, but there's maybe dozens of papers about the theory of VI, and there's a lot of wide open theoretical questions about the quality of these estimates, how to optimize this properly, what guarantees you might have, how to balance the fidelity of the model against the data, against the optimization problem. There's many, many interesting statistical and optimization-based theoretical questions around variational inference. Oh, my computer died on this. Yep. Oh, that was exciting. Sorry about that. Oh, it died. We know where it died. Something's wrong with the slide before this slide. Sorry, I just killed it on purpose again. Anyway, I have a couple of slides that usually work, this one, that talk about some recent work we've done in VI. This is one that looks at an alternative measure of closeness, one based on the score, the expected score. This is work with Diana Kai. Here we're looking at expanding the class of distributions. So this is with my student Bohan Wu. So instead of a factorized family, we think of the entire family, but then we regularize to be close to the factorized family. And it gives us a way to trade off kind of the fidelity of the variational family with the complexity of the optimization problem. This is some work we're working on now. And I didn't mention this, but that reparameterization gradient is the core machine inside the variational autoencoder. All right, so the variational autoencoder, if you really think about it, is two things. One is a deep generative model. Z comes from a standard Gaussian, goes through a neural network, spits out a distribution of X. And the other is a variational family. But that variational family is what's called amortized. It itself is a neural network that takes in the data point and spits out optimized variational parameters. And fitting those, the parameters of that neural network, which is commonly called an encoder or an inference network, that's the world of amortized variational inference. And so we've been thinking about that as a more general inference strategy, but that's also a wide open and interesting area in VI. Okay, here are some papers from our group about VI. Thanks very much.